welcome to the University of Urbino. Togliamo la mascherina. It's a pleasure to have you here. We are here to award two colleagues, Professor Victor Pambuccian and Vincenzo De Risi. They are being awarded by the Comandino medal and the Del Monte medal. These two medals are assigned on the basis of their work on history of science and fundamentals of science. And we are very happy that we are able to do it in present this year. And so these are the awards that were supposed to be assigned last academic year, 2021. Let me read the two motivations for their work. So the first medal has been assigned to, again, Professor Victor Pambuccian, and for his contributions to the comprehension of the foundations of geometry, through which he highlighted new and important results, often turning an explored path into fertile grounds for research. Thank you. And the second motivation is for the on which has been based the awarding of the second medal to Professor Vincenzo De Risi for his contributions to a rigorous analysis of the concept of space and its historical and theoretical development, and for the advancements he made possible on the comprehension of ancient and modern geometry. Thank you. So, Professor Laerte-Sorini, the floor is yours.
I'm very pleased to represent the Center of Studies Urbino e la Prospettiva, especially on this occasion in which two distinguished professors such as Victor Pambuccian and Vincenzo De Risi are awarded. As you know, it is the 600th anniversary of the birth of Duke Federico, and this mainly thanks to his clever contribution. If today we can talk about Federico Comandino medal and the award destined for career development, and Guidobaldo Del Monte medal, which is intended for young researcher, and an ideal line between master and disciple. In fact, Duke Federico has the intuition to create a place similar to a crossroad of art and knowledge, a meeting place between art and science, a place in which new forms of art were born. Our Center of Studies has a 20-year history during which it has the audacity to follow the Duke Federico's legacy by promoting knowledge, organizing conference, film review, seminars on the subject of science. And this dissemination within the center, we also publish a prestigious review of book. We won national and international projects such as Formelle of the Ducal Palace of Urbino, one of the best Italian-founded projects, and we organize international exhibitions such as the one entitled Sapientia, Pietias et Otium al Tempo del Duca Federico, which will be inaugurated on June 4 at the Albani Museum, and we give a prize such as those we are assigning here today to Victor and Vincenzo, who join the list of well-known colleagues already awarded, such as Reviel Ness, William Renechea, Enrico Gamba, Sir Roger Penrose, Jürgen Rand, and many others. The mission of the center is today confirmed in creating a network of people and disseminating their common knowledge with an activity of public engagement impacting on social welfare. Thank you all for being present, and long life to the center Urbino La Prospettiva. Now, Vincenzo Fano.
Thank you very much, Laerte. I am here bringing the greeting by our head of the Department of Pure and Applied Sciences, a department in which science and history of science, philosophy, logic are together. It's an interdisciplinary department here in Urbino. We are very happy of having here in Urbino this department. And Urbino was in 16th century a place where Federico Comandino and Guidobaldo, two very distinguished scholars, build a sort of bridge between humanities and science that is also today living. Federico Comandino and Guidobaldo were scholars, very good mathematician and physicist, at the same time also very good scholar in ancient literature. They are able to understand Archimedes, Euclid, and so forth. So they brought in the modernity, the thinking and the work of these very important scientists of antiquity. From Guidobaldo and Comandino, Galilei take the step and begin the scientific revolution, a very important event in the general history of Europe. So in Urbino we have these two medals, and I am very happy that two medals, one for the career, one for the early career in history of science here in Urbino, and I am very happy that Jan Pambuccian, that is now our visiting professor in Foundation History of Geometry, and Di Vincenzo, that was, before the pandemics, visiting professor, also with us for many months in Urbino, giving courses in history of science. I am very happy that both received today this important recognition on history of science, and I hope that this discipline will be more and more important in our university. Thank you very much.
Okay, the program go on with the Lectio Magistralis of Victor Pambuccian. Okay.
I am going to say a few things about being a geometer, one that doesn't use any other methods but those of geometry. and about the fact that Comandino is still very much of relevance today, that the project of becoming Greek isn't one that is accomplished ever. So where does the title of my talk, which is what uses a geometer in times of need, it comes from Hölderlin's poem, where he says, und wozu Dichter in dürftiger Zeit? Aber sie sind, sagst du, wie des Weingotts heilige Priester, welche von Land zu Land zogen, in heiliger Nacht. This he wrote around 1800, but it was unknown for most of the 19th century. It was discovered in about 1894. In English translation, this would sound like, what use is a poet in times of need? But you will say, they are like the holy priests of the wine god, moving from land to land in holy night. Now, what was Hölderlin referring to by the times of need? What he was referring to, which comes out of the very long elegy, is the absence of gods, what we would call disenchantment. So what's the connection with geometry? I mean, is geometry poetry? The way I understand it, it is pure poetry. Why is it poetry? Well, because it creates a world out of words, just like poetry does. And it is pure because it's independent of these languages that come and go, where about every 800 years they become incomprehensible. In other words, we can still understand what Euclid meant, unless you are a very extreme purist and you think that only a Greek can understand that and nobody understands it anymore. But in general, we can say that we can still understand what it's about. Although poetry from that time, unless you're an expert in ancient Greek, and even then, you wouldn't have the context and the times, the really living then, we can consider them gone. So what are the times of need for somebody like me? Oh, I'm born way after there were no more gods and many other things. So it's more troublesome than times of disenchantment or the loss of cultural references that T.S. Eliot deplores in his Wasteland. It's the fact that one knows by the time one graduates from high school that one doesn't need the hypothesis of nuclear weapons for the end of civilization. The fact that peaceful, everyday living suffices to bring it to an end. So the times of need are more immediate than the times of spiritual need. So what does one do in this kind of situation? Well, on a private level, one tries to choose a refuge into something where one wouldn't contribute to the direction of society that one disagrees with. But isn't pure mathematics enough of a refuge? Why choose geometry? Well, pure geometry is pretty much on the demise for ever since the 17th century, let's say. And this, I think, is a kind of disenchantment inside mathematics. So what do I mean by pure geometry? I mean, a geometry where only geometric axioms are allowed. In other words, you can't use algebra or other means, embellish it with more than purely geometric thoughts that are encapsulated in axioms. The decline was marked in the 19th century already, where a so-called arithmetization set in. In other words, the idea that all you need is the natural numbers, that all of mathematics can somehow be subsumed to that. But the decline started in the 17th century. I mean, Newton complained about it. What are its competitors? One can't say that geometry disappeared from the picture. It still exists, but it exists in the versions of differential geometry, topological geometry, algebraic geometry. So the first two, differential and topological geometry, stem from a belief that continuity is an essential component of the actual outside space. Algebraic geometry has a completely different origin. It likes what it can do with a very powerful algebraic apparatus. That is a completely different thing. I don't think that anybody in algebraic geometry believes that the space outside us gives us some kind of clues that we should work in fields in which every polynomial has a root or something like this. I doubt that. Now, the justification in working in these and not working with pure geometry is manifold. One would be that, well, working in pure geometry is like deciding to climb a mountain with just the things you can do with your own hands. You can't use boots that are bought and produced by synthetic fibers and so on. Everything has to be really done by yourself. And you can't go by helicopter. So it sounds like some kind of Luddite. I mean, you're against the times because things have developed and now we have these tools. Why would you be against them? So this is one of the reasons. The other is that geometry is, after all, supposed to be useful, supposed to be describing some outside reality. And that outside reality, the line of reasoning goes, would be akin to the geometry described by differential geometry or topological geometry. Well, David Hilbert already in 1898 knew that that's not the case. He wrote that a homogeneous continuum that would allow indefinite divisibility and would thus achieve the infinitely small cannot be encountered anywhere in nature. The infinite divisibility of the continuum is an operation existing only in thought, only an idea, which is refuted by our observation of nature and by the experience drawn from physics and chemistry. Meanwhile, another approach has appeared which solidifies Hilbert's take on the difference between our mental notion of continuity, the idea that there is something where space is not like a string of beads. It's not something that is one after the other, that there is continuity, that time isn't some kind of a movie where you have sequences one after the other, that it is a continuity, not a discreteness. And this is truly a time of our mind and a space of our mind, but does it correspond to anything outside it? Well, loop quantum gravity, which it's a field established by Carlo Rovelli, seeks to unite Einstein's theory of general relativity with quantum mechanics. And according to loop quantum gravity, the universe is not continuous. It is composed of elementary grains or quanta of space. So in other words, it's very different from what differential geometry or topological geometry tells us. People have thought that you can check in the outside world things that your geometry tell you are so. And they have confused the objects of reality with the objects of mathematics. This confusion still is prevalent when you're thinking that geometry ought to describe the outside reality. A German astronomer, Friedrich Zöllner, in 1877, thought to prove that there is a fourth dimension because he thought these mediums who disappear things or who do all kinds of crazy things would be justified if there is a fourth dimension. Then objects appear and disappear the way they would appear and disappear to a two-dimensional being. You put this here and it appears, and you take it and it disappears. So the same thing would happen in 3 dimensions. So did it work? Well, no, it didn't. He tried some things because usually people disagree with the observations of people in seances. So he thought of producing objects that you could put in some kind of a museum, and everybody would agree that that says that there is a fourth dimension. And one thing he tried to do was to give the medium 2 rings, lifesavers of sorts, made of different kinds of wood. And if this medium would have succeeded in interlocking them like this, then that would be it. If you saw 2 interlocked rings of different kinds of wood, then, well, they have to be interlocked through a fourth dimension. The other thing that he had attempted to show was, gave the medium was a candle and an empty glass sphere, which was closed. If you manage to get the candle into the sphere, well, then that's again proof, because, a hollow sphere has to be blown. It's hot. The candle wouldn't stay intact during the process. They didn't work. But it's worse that they didn't work. Even if they had worked, the assumptions that these things, that the objects of reality are like things in our geometry, is kind of far-fetched. In 1994, in the Journal of the Society for Psychical Research, a journal that was founded in 1884, it was a paper by Song-Kong Ji, who described the contents of a film that got the 3rd prize at some Chinese scientific film competition, where a medium looks from a distance at a jar, a closed jar that has pills in it. And it's done with, I don't know, 1,000 sequences a second or so. And it shows how the pills go through the wall of the bottle and come out. Some break, others come intact. Okay. Well, I asked a physicist friend, I said, from my point of view, this isn't a big deal because the pill and the jar, they're mostly made of holes, right? I mean, matter isn't what it seems like. I mean, an atom is full of, spaces to go through. He said, no, there are forces that prevent this from happening. So the textbook doesn't like this at all. And that reminded me a story that an oncologist was asked on public radio some 20 years ago why he underwent chemotherapy another 20 years earlier for a tumor that was known to not respond to chemotherapy. So why would he subject himself to this? And he said he hoped that the tumor hadn't read the textbook. So I guess the pills and the glass bottle also didn't read the textbook, so they decided to do that. Whichever way it is, it shows that these things, the idea that geometry describes something out there, is vastly exaggerated. For example, when we're saying differential geometry, we look at some derivative. So the essence is that these functions that form the atlases for differential geometry should be differentiable. And we choose the classical form of differentiability, which you see on the picture. However, there is another differentiability introduced by Peano in 1892, which you see below. It looks very similar. In fact, Peano thought that this portrays the concept of the derivative used in the physical sciences much more closely. So why don't we use this one when we describe, our surfaces and our manifolds in differential geometry? Well, because we have a great theory regarding regular differentiation and a very poor one regarding Peano differentiation. If we chose Peano differentiation, all of differential geometry would collapse. So in other words, we choose our theories because we're good at them, not because they correspond to anything out there. Now, these things are not new at all. In fact, Giordano Bruno told us these things in 1584. Altro è giocare con la geometria, altro è verificare con la natura. And something similar is what Einstein said in 1921. He said, as far as the laws of mathematics refer to reality, they're not certain. And as far as they are certain, they do not refer to reality. Which is exactly what Bruno had said. But somehow people are more surprised by Einstein than Bruno. However, Einstein also thought in a certain sense that nature should listen to our theories, because Ilse Rosenthal-Schneider tells us that in 1919 a telegram had arrived from Eddington, who had gone on this famous solar eclipse expedition confirming the predictions of relativity. And Einstein asked Rosenthal-Schneider to read it. And she said, how beautiful, it's almost the value you computed. And Einstein said, I knew that the theory was correct. Did you doubt that? No, sure not. But what would you have said if the confirmation had not come the way it did? In that case, I'd pity the good Lord, for the theory is correct. Da könnt mir halt der liebe Gott leid tun, die Theorie stimmt doch. So, although in the previous quotation, he tells us that, we should separate the two, in this one, he is of the opinion that, well, no. So I think we can conclude that the excuse that we need to use these things because they reflect the outside world is vastly exaggerated. we can safely conclude that the real numbers, the way we know them, and which rely on set theory, a late 19th century invention, are not read off some outside reality. So that the geometry we have and the continuity we have is an inner reality, not an outside reality. So what happened to today's mathematics? Of the two fundamental intuitions, at least in Kant, of time and of space, only the intuition of time forms the basis of contemporary mathematics. The geometry in use today is built upon a foundation involving the set of real numbers, which originates in the intuition of time, or on an algebraic foundation, which also involves time, because an algebraic operation is being performed in time. So all of mathematics becomes a story about operations. It's computational, I would say disenchanted in this form. Isaac Yaglom in 1984 wrote that the algebraic geometric diet amounts to two alternative languages, and it is as fundamental as that formed by analytic and synthetic arguments, and that formed by the rational and the mystic approach, or that formed by the left and right halves of the brain. So by having cut ourselves off from the geometric side, we have eliminated the mystic approach in the right half of the brain. So the mathematics taught in school today almost doesn't contain any geometry. And we'll see that this has consequences, I would say. What Comandino did with his work, and it's an immense work because for about 1,000 years, Europe was asleep, mathematically speaking, and it woke up with his enormous work of translating everything, including things that the Islamic mathematicians did not know much of, like Pappus's collection, for example. So what Comandino tried was to become Greek. The question is there a substance to this, to Greekness? So what is the alternative to Greekness? I think it is what the Greeks called barbarian, but not in their understanding. Their understanding was that you are barbarian if you don't speak Greek. Well, that's very superficial, I think. Whether some specifically Greek things, some things that they and only they came up with. And I think we can find two such things. One is the Exomatic Method, in which a domain of thought is organized by singling out a few key pronouncements, and everything else is deduced. So the realization that theories are narratives on their own, most clearly expressed in the field of mathematics, but not only. And the second characteristic is an emphasis on the importance of history. Sure, you might say, well, the Chinese and the Egyptians had their own histories, but their own histories were basically names of pharaohs or who the strong people were. Well, that's very different from what the Greeks did. Here we have a historical recording of what happened in a meaningful narrative, not just names and won this battle and that's it. So as I said, what Comandino did was clearly thinking that this is something worth doing. This is a question of taste. It is impossible to say whether one is better than the other. whether to be Greek is better than to be barbarian. It's so the idea was that introducing this approach in education, Italian and by extension Western culture opted for this Greek approach. And it has had a significant effect on the later history. Now, Western culture, if there is anything that is under that name, has two origins. One is Athens, the other is Jerusalem. Athens can form the basis of a cultural heritage because the Greek approach can be taught, and it has been taught, both in Greek times and in modern times. The position toward life and the world originating in Jerusalem cannot be taught. Or as Krishnamurti emphasized, there is no right guru. There is only wrong guru, because nobody can teach you what you are. So the spectacular failure of teaching the ethos originating in Jerusalem was not a historical accident. It's something you can't do. And vice versa, you can have people like Francesco of Assisi, who, without knowing Hebrew or Greek or Aramaic or Pali and never having heard of the Buddha, figured it out on his own against his time, which contained no indication that that's the thing to do. Whereas in the Greek way, we don't have any example of a Pacheka Buddha, which is a Buddha who out of himself, without having seen, without having without having heard of any kind of doctrine, would find out the truth about life. In the Greek way, we don't have any such example. We have Ramanujan, for example, who was able to invent an enormous amount of mathematics. Not having paper, he wrote them down in notebooks, only the results, one after the other. And it took about 40 years of the best mathematicians to make sense of what he wrote and to prove it. We have no idea how he proved these things. He told us that the goddess Namagiri Thayar told him all these things. We have the example of the Japanese mathematicians who have these wooden tablets at the entrance of temples, the Sangaku problems, which are very complicated geometry problems, but with no hint of a proof. They're all correct. We don't know how they found them. So independently, we haven't seen anyone coming up with the Greek approach out of themselves. It's something that you have to culturally have heard of. It's pretty much like music. I mean, you can be Clara Haskell, and if you have no piano invented, you won't be able to play. Perhaps you will be if you don't have a teacher, but without a piano, surely not. And I think that the Greek heritage is like the piano. You can't invent it. So it's something that happily can be taught and need to be taught if it is to survive. Now you might say that I just made up these two origins, that they're kind of have nothing to do with Western civilization. It might be an accident, but perhaps not, that the only two university professors in all of Germany who refused in 1934 to swear the Hitler Oath were Kurt von Fritz and Karl Barth. The first was a Greek classicist, and the second one was a Christian theologian. They both lost their university positions. So the question is, isn't this all ancient history? I mean, what relevance can Comandino have today? I mean, he was in the business of humanism. Did we not graduate from humanism the way we graduated from elementary school? Didn't the age of enlightenment follow? And didn't we even graduate from that, like from middle school? Well, let's see what Kant said that enlightenment is. He says the enlightenment is man's emergence from his self-imposed knowledge. Knowledge is Unmündigkeit. Knowledge is the inability to use one's own understanding without another's guidance. This knowledge is self-imposed if the cause lies not in lack of understanding, but in indecision and lack of courage to use one's own mind without another's guidance. Dare to know. Have the courage to use your own understanding is therefore the motto of the Enlightenment. Laziness and cowardice are the reasons why such a large part of humanity gladly remain minors all their lives, long after nature has freed them from external guidance. They are the reasons why it is so easy for others to set themselves up as guardians. It is comfortable to be a minor. If I have a book that thinks for me, a pastor who acts as my conscience, a physician who prescribes my diet, and so on, then I have no need to exert myself. I have no need to think if I can only pay. Others will take care of that disagreeable business for me. Well, I leave it to you to think if we have graduated from this. Can a culture who has adopted Greekness fall back into barbaric thought, or does it live on automatic pilot? You don't need to do anything for it. Or is it something that needs to be continually fought over? Because the lure of a barbarian lifestyle is very strong. I mean, you don't have to have the weight of history on you because you don't think historically. Everything happens now. All your thoughts are valid because they come from you, and what better origin for them to be true. You don't need to go through these painful questioning of things and figuring out what the axioms of your thought are and all of these things. After all, the hero of this Greek thought, who Socrates, knew only that he didn't know anything. So it's a very poor hero for the ego who tries to know things and understand things. So perhaps staying Greek is an everyday struggle, as Patricia Boisson-Schnoropian once told me. She is a specialist in medieval Armenian and has translated a lot of medieval Armenian texts, including two histories of Armenia from medieval times. And she told me, l'arménité, c'est un combat de tous les jours. For her, the combat was that she had to raise 3 kids with Armenian as a language in a suburb of Paris, which is un combat de tous les jours. So we're perhaps too Faulknerian. We think that the past is never dead. It's not even past. But if we look, for example, at what Dostoevsky wrote in 1880, but God will save his people, for Russia is great in her humility. Smyrenia is a bit more than humility. Well, about 37 years later, this was lost. The past was completely dead. So the idea that somebody does something once for you and then you can just go to sleep because Comandino was then and we're doing fine, I think is a major mistake. There's also a mistake, and I've noticed this when I talk about the Greeks, that one thinks that one is smarter than them because, well, we know so many more things and we have so many more gadgets. Well, Littlewood once told Hardy that the Greek mathematicians are not clever schoolboys or scholarship candidates, but fellows of another college. So thinking of them as some kind of primitives in their mathematics, as some kind of thing that you graduate from, is a major mistake. So translating the elements is one first way to enter the Greek world. Here you see a translation from the 7th century. The manuscript is from the 12th century in Armenian. Here you see Comandino's 1572 Latin translation. And as I said, in school mathematics, this is not encountered anymore for various reasons. One is that one should have a happy childhood, and certainly going through all this is not very happy. And what has it been replaced by? Since we don't have geometry, well, it's a lot of what I would call Babylonian mathematics. The Babylonians were great at computations and numbers. The Greeks were very bad at these things. There's no mystery left in mathematics at all. Just the part that a computer does better than a human is all that's left. What's the purpose of this? I mean, I myself have never used mathematics in real life. The idea is that these people will. Perhaps they will have lives where they use them. I didn't. What is it? To increase perhaps the shame of not being a thing, which Günther Anders sees in his Antiquiertheit der Menschheit, Des Menschen of 1956, where he sees a second level of alienation, that on which man has recognized the superiority of things, brings himself in conformity with them, approves of his own having become a thing, respectively condemns his not having become a thing as a shortcoming. So my point is that if one were to teach geometry, because geometry cannot be done by machines, one would restore the dignity of being human and of having creativity. What we're teaching is just teaching that we're worse than our machines. It's part of idolatry. Now the question is geometry not disappearing, did not disappear because it had exhausted what it had to say? Didn't we become too good at it? And what's the point in doing more of that? Well, no, not quite. Euclidean geometry has something that is called similarity. You can have a small triangle and a big triangle. Something you see when you go to a copier machine and you put some percentages there to shrink it or to magnify it. You expect the shrank thing or the magnified thing to be the exactly same thing, only to a smaller scale. Well, this is a particular quality of Euclidean geometry. However, in 1831, János Bolyai had defined something called absolute geometry, which is a geometry true in Euclidean and non-Euclidean geometry, where certain assumptions of Euclid, the parallel postulate, and also what follows from it, things like the existence of a rectangle, are not assumed. So it's a core geometry that is agnostic regarding the existence of similar triangles. So no similarity is allowed, which means there's no room for computations in it. Discovering truth in absolute geometry is extraordinarily strenuous. However, most things are true there. So when one does geometry in this way, one obviously is a poet also in the sense of the saying from Joseph Brodsky, that a poet writes to please his predecessors, not his contemporaries. And how does one speak to the ancestors is what Jorge Teillier tells us. Para hablar con los muertos hay que elegir palabras que ellos reconozcan tan fácilmente como sus manos reconocían el pelaje de sus perros en la oscuridad. So in order to talk with the dead, you have to choose words that they recognize as easily as their hands recognize the fur of their dogs in the dark. So whenever I wrote things that I thought would interest my predecessors, and they were dead, mostly Friedrich Bachmann and other people who were interested in this pure geometry. I wrote in German, but the last one was in 2004 because afterwards nobody would accept a paper in German. So now I can no longer follow this. Let's look at examples of things that ought to be true without these Euclidean assumptions. So following the example of his mentor, Federico Enriquez, whom he met as an engineering student at the University of Bologna, Oscar Chizzini was actively involved in the teaching of mathematics at the secondary school level. He held the position of editorial secretary of Il Periodico di Matematiche in 1921, when Enriquez became its managing editor. And after Enriquez's death, Chizzini held the managing editorship for the rest of his life. In 1925, another mathematician with an interest in elementary mathematics, Alessandro Padua, who's famous in logic, published a note in the Periodico in which he proved by using elementary inequalities that of all triangles with a given parameter, the equilateral triangle has the greatest radius of the circumscribed circle. In a paper appearing right after Padua's paper, Chizzini provided a purely geometric proof of the validity of the theorem in plain Euclidean geometry over real numbers, rephrased as, of all triangles inscribed in a given circle, the equilateral triangle has the greatest parameter. In 2007, after thinking about this problem for about 3 years, I could show that it is true in absolute geometry. So, first of all, there's a lot of things you have to do before showing this. First of all, there has to be an angle of 120 degrees in absolute geometry so that there is an equilateral triangle inscribed in your circle. That's not an easy thing to do. I happened to do this in 1998. So let's look at what it says here. So you have here a circle, and of all the triangles that you can inscribe in this, so pick any 3 points on the circumference, you get a triangle. Well, which one has the biggest parameter? Well, the equilateral one, and you would think this has nothing to do with the Euclidean nature. This has to be a very general thing. All you should be able to do is you should be able to put these 3 sides of your triangle back to back to form the so-called parameter and to be able to compare them. Well, that's pretty much what absolute geometry does. It allows you to do that. So, to me, the proof in Euclidean geometry is a good first step. When you have no other proof, it's fine. But in time, you should always look for the difficult proof, the one in absolute geometry. Well, why is that? Well, suppose you prove something, a certain property that you think are of humans, and you use for that property the fact that humans have flat nails. And it's essential in your proof of that particular property that humans have. It turns out that the property is common to all mammals. How ridiculous would your proof be then when you're using a particular flat nail story for this property that is true of, cats, dogs, and others who have no flat nails? That's exactly the same story here. When you have a proof in Euclidean geometry that is fundamentally Euclidean, you have masked, you have obscured the true reasons why that thing is true. So you have a hope that it's going to work, but until you know how it works, you don't know the true reasons for that. You have the wrong reasons. You have the flat nail reasons for it. Now, Comandino has a work on centers of gravity. And I'd like to show that that is as relevant today as it was then. So, if we think of a system of material points, so think of points, and every point has some mass attached to it. And you can join two such systems and create a bigger system. Now, that's what that says. And to any such system of points, you call a center of gravity something that satisfies a few conditions. The center of gravity of just one point with a certain mass is just itself. That's clear, right? That's what you want the center of gravity to do. If you have 2 points, A and B, each having the same mass, then the center of gravity should be in the middle, and you don't say what the mass should be there. You expect, because you have this Euclidean thing, that it should be the sum of the masses. I'm not asking for that. Whatever mass, but just asking that it be in the middle. Now, if I have 2 points and whatever mass here and whatever mass there, then the center should be on this line. That's a reasonable thing, right? You expect the center of gravity to be on that line. The next one is that if I have 2 systems, then I can do always the center of gravity of one system, of another one, and then do the center of gravity of what I get. That's the 4th condition. There's an additional axiom, additional condition that you may ask, which is no longer absolute, which is of Euclidean nature. It says that the center of mass should not depend, the mass associated in the center of mass should not depend on the masses of the 2 objects. So I have an A with a mass M, a B with a mass B. And there is somewhere a center of mass of this system. There is a certain amount, K said, associated to it. Now I have 2 other points, they may be at a much bigger distance. And I'm saying in the center of mass, which is wherever it wants to be, there should be exactly the same amount. So the amount doesn't depend on the distance. This is not true in the non-Euclidean center of masses. Center of gravity that satisfy the 5th axiom as well will be called strong. So if I assume that I have only 3 points, that the centers of mass exist for systems of 2 or 3 points, and the 3 points should have the same mass attached to them, then I get nothing. I get no Euclideanity. Yeah? That this is so was proved by Johannes Jelpslev, a Danish mathematician in 1929. Why? Well, he showed that the medians of a triangle are concurrent in absolute geometry, in a very weak, actually, absolute geometry. So if we allow 4 points of equal weight, the points can be also not differential, then the existence of a strong center of gravity implies Euclideanity. Maria Teresa Calapso, a mathematician from Messina, has shown this in 1971. She showed the following thing. If you have the picture that you see there, where M is the midpoint of OA, N is the midpoint of OB, C is the midpoint of AB, then, and P is the midpoint of MN. If you have this, this is a given, right? So given the points O, M, A, B, C, N, P, with M midpoint of OA, N midpoint of OB, and C midpoint of AC, and P midpoint of MN. Then OP and C should be collinear. That's enough to imply the Euclidean nature of the metric. In other words, there exists a rectangle in this case. What does it have to do with weights? Well, think of two systems, A and B. A is made of O and A. In both is the same weight, mu. And B is the system made of O and B. In O and B, it's the same weight. Now bring the two systems together. You will have now twice 2m in O. You have 2 mu in O. You'll have a mu in A and a mu in B. And if there is a center of gravity for this system, then the things are happening like in Calapso's axiom. Why is that? Well, think of the center of gravity of O and A. It should be at M. Of O and B, it should be at N. Now in M and N, there are the same weights, because we've said that axiom 5 holds. It doesn't matter how far you are. If you have the same weights there, it's the same weight there. So the center of gravity of M and N is at the middle point, so at P. Okay, so we computed the center of gravity of OAC, OAB in a certain way. Now let's compute it in another way. First compute the center of gravity of AB. That's C. So now OC has the center of gravity somewhere on the line. And we're done. So it means that the P, which has to be the center of gravity of the system, is on the line. Pierre Varignon's theorem also implies Euclideanity. Pierre Varignon's theorem just says that the two things that you see there intersect in the midpoint. That's again something that implies Euclideanity. And it has again that midpoint there that you see, the middle of everything, would be the center of gravity of this system. I don't have time for this. So here is another thing where the center of gravity can be said to be essential in proving that a space pentagon that has all sides and all diagonals congruent must be flat. This is important for chemists. And you can show it with hardly any axiom except for the assumption that any system of 5 points has a center of gravity. Now, to end this talk is Comandino's own theorem. What does he say? He looks at the center of gravity of a tetrahedron. So you have 4 points in space, and he says, you compute the center of this by doing the medians of this thing. Well, what are the medians? Let me show you his picture. okay? So you join a vertex of the tetrahedron with a center of gravity of the opposite face. There are 4 such. His theorem says that these 4 meet. The simplest proof is one that uses Menelaus' theorem and can be done in 1 line. Now, there are several axiom systems for a very bare bones absolute geometry in which all you have is symmetry in planes. This should be true there. Well, why? Well, I have several reasons why, but nobody has shown it is. So we don't have the right setup for proving this theorem that goes back to the 16th century. So it is an open problem to show that Comandino's theorem requires just a very bare bones absolute geometry of 3-dimensional space. That's it.